Hello, Inzamul, can you hear me? Or who is there in CET?
Sir, I can hear you.
Ah. So you can tell us when to start, or
Yes, sir, you can start now, sir.
you can start?
Yes, sir, you can start now.
All right, good. Okay, so welcome to this first session, live session of the course, Nuclear and Particle Physics. First of all, thank you all for showing interest in particle physics and nuclear and particle physics as such. It's very interesting. At least it is very interesting to me, and I hope it's also interesting to you all. One of the main reasons that I am personally interested in this, I like this, is because we are actually talking about the building blocks of the universe, in the sense that all matter around us are made of a few fundamental particles. It's amazing, actually. There are a variety of things that we can see around us, and there are things which are beyond the terrestrial domain and beyond the solar system and beyond our galaxy. We have observed all of those, many of those things. And the interesting thing is that all of these matter are made of a handful of elementary particles. And that's amazing. Like, I mean, it's not some kind of a theoretical idea, um, just a theoretical idea. It's, of course, there is a theoretical idea, but it is supported by very precise. When I say very precise, it is basically some of the measurements in the particle physics are the most precise measurements in the whole of experimental physics or even other domains of science. For example, the alpha, the coupling constant, electromagnetic coupling constant, or the fine structure constant, as we call this in the atomic physics, is measured to a very high accuracy, up to, I think, some 10 power 13 or some such thing, 10 power minus 13. So many digits, which means that if you put a 0 point and then go up to something like 12 to 13 digits, and we can actually say that we know those digits without uncertainty. So such precisions, and this is true with many other measurements. And therefore, so far, we have a very good confidence in the theoretical framework, or the model that we believe is the particle physics or nuclear physics model. Well, particle physics model especially, that is true to a very good. I mean, to a very good, very precise. I mean, at a very highly at a high precision measurements have supported this thing. So this is something which actually gives us the confidence in saying that we know that all things in the universe are made of a few elementary particles, and the dynamics of these particles, or all of these things, are dictated again by four fundamental forces. So it's amazing to me that that is the case with the whole of the universe. In fact, the universe is so large and varied, and the all of its dynamics is dictated by a few fundamental interactions of the elementary particles that build the entire thing. In our course, we started it with the nucleus, which itself is something which is new in the sense that it is just 100+ years the idea of nucleus and the atomic model that as we see it now is with us. With the experiments of Rutherford, etc., that we know that there is the atom has a nucleus where most of the mass is concentrated, and all the positive charged particles are there in the nucleus, etc. And so that engaged as the study and understanding the properties of these nucleus um, was our interest in the first part of this course, which we have kind of covered, I think. Now we are going to the elementary, the more fundamental levels, like what are the nucleons and what are the properties of that, and then we see that they can further be understood as made of more fundamental particles called quarks. And electrons, by the way, are elementary. So far as we know, there is no structure to the electron, but the proton is made of 3 quarks. And there are many other particles similar to the protons and neutrons, which are also there, which are discovered in the cosmic rays. Cosmic rays are the rays, the charged particles streaming out from or into the earth from outside. It could be, I mean, part of it is from sun within the solar system, and then it is also from outside the solar system. It could be primordial things or coming from galaxies, various things, etc. So there have been a lot of studies. Even now, there are a lot of studies which are going on to understand the cosmic rays, its interaction with the upper atmosphere, the atmosphere of the Earth, and that gives us a lot of information about these particles. So now, even initially in the beginning, like I think we have discussed that when we discussed the quark model, that it was not understood what these particles are, but now we know very clearly that all those particles can also be thought of made of quarks. So fundamental particles involve only quarks, and electrons and particles like electrons, collectively called leptons. So then a good understanding of these elementary particle dynamics and nuclear physics also, nuclear dynamics, is certainly important to understand the universe naturally, right? And in fact, now it's almost, it is established. I could say that, think that it is now established without much doubt that the universe started like highly dense in a highly dense state and then small in size, much smaller than what we are now, and then it expanded and cooled down and became rarer, and density became smaller, and it expanded, and then as it expanded and cooled down, and then lumps of particles, that the matter actually got accumulated in places, and these kind of structures, various different structures that we see now, like the galactic clusters and galaxies, etc., and our Earth and we all were formed from such a highly dense form of this nucleus, of the universe, and that is the Big Bang cosmology. So we have very good, we have enough proof to actually believe that that is the case. For example, you must have heard about the cosmic microwave background radiation. This cosmic microwave background radiation is something which pinpointed or clearly told that the picture that the Big Bang cosmology has put out for us is believable. And then, and so there, when we talk about the highly dense early stages of the universe, there are no structures like us or even galaxies, but there were these quarks, and that is expected to be in a kind of a quark and gluon. Gluons are basically the equivalent of photon in the case of strong interactions. And so we have the electromagnetic interactions. Electromagnetic interactions are mediated by the photons in the quantum theory picture. And similarly, the strong interactions, we talked about the strong interactions. I'm sure you're familiar with that now, by now. And strong interactions are mediated by what's called gluons. That's it. So these, so in the very early stages, it was kind of a mixture, okay, of gluons and quarks. So it's basically, that is why it's called a quark gluon plasma. And there were no atoms. So atoms were formed much later in the evolution of the universe. And before the atoms were formed, the nuclei were formed. So the nucleus synthesis would be dictated by the rules of the nuclear dynamics. So that's where, for example, how the two protons combine to give deuterons, or how the protons and neutrons combine to give you helium, and how the helium combines with the other protons and neutrons to go to lithium, etc. So the heavier and heavier nuclei were produced in the early universe. We could not go beyond lithium, really. So that only light elements could be produced in the early universe. But there, the understanding of our nuclear physics, when we put in there, we can actually understand the evolution of the universe also. Or the other way, the evolution of the universe will be dictated also by these nuclear reactions at that time. So, for example, how much of the helium would be there produced? Okay, and is there any way to actually measure or find that out? There are ways to actually find how much of the helium could actually be surviving the relic density of the helium, etc. We can measure that, and all those observations would give a good understanding of the early universe in a way. Okay, and further on, there are observations based on this cosmic microwave background radiation, which also gives independently the information about the relic densities or the amount of the protons, etc., that are supposed to be there initially. Okay, so these or and the nuclear dynamics, etc. And so now, what we know now is that all these kind of things, that atomic physics and related nuclear physics and things after that, is kind of fairly understood in the cosmic scenario. Electroweak interactions, we can't really have a direct test of that in the observations based on the cosmology, or we cannot have a direct test of this electroweak interactions based on the cosmological observations yet. But there are a lot of implications of that. For example, according to our present quantum theory of electromagnetic interactions and weak interactions and nuclear and strong interactions, Okay, everything, all particles have to be created in pairs of particles and antiparticles. If you create an electron, you cannot just create an electron. First of all, the charge will not be, I mean, initially there was no the electron. And if you create only one electron, then the electric charge will not be same in the initial and final state. So that's not something which we want to have. So the charge neutrality of the universe demands, that is one of the things that itself demands that particles and antiparticles are made in pairs. And not only this electric charge, various other charges, like for example, the strong interaction or whatever is the quantum number related to the strong interaction, weak interaction, etc. All of those things have to be also balanced. So for that, we need a particle and an antiparticle because the antiparticles will have the opposite charges usually. So now if they were created like that in pairs, then what happened to all the antiparticles is a big question now. We don't really have an answer to that. So we just put all these uncertainty or ignorance in what we call the Barium Asymmetry of the universe, and that's something which is actively being researched now. For a long time, we knew that this problem is there. I mean, just once we know what quantum theory of elementary particles is, then immediately this question came. So if the question is there, like what is the way to actually generate this Barium asymmetry? It's called Barium asymmetry because mostly the matter consists of protons, etc. Electrons have negligible mass. So the majority of the mass or particles and the mass of the matter in the universe when we are talking about, it's basically the baryon. So the baryons are there, but anti-baryons or anti-proton, for example, anti-proton, anti-neutron, etc., are not really seen. Well, we do have them, a few of these things in the cosmic rays, etc. We can generate them, we can create them in certain reactions, but it's not like there are structures, galaxies have large concentration of these antiparticles. One of the things that happens is that if there are antiparticles and particles coexisting, then they would annihilate, and then a lot of energy would be released. And then people have been actually looking for such things also. If there are focus areas where particles and antiparticles are getting annihilated, and then large amount of energy is released, etc. So far our conclusion is that the universe is by and large made of only the particles or the baryons. So that's one of the things that's not really known yet. And there are also other things some of you may have heard about. It's called the other type of particles, which are not interacting like the particles that we know. They don't, without, see, how do we observe things? We observe most of the things, the galaxies or other things, cosmic objects, by looking at them through the electromagnetic radiations. Okay, it could be X-ray, gamma ray, or whatever the wavelength is, or optical wavelength, but it's basically the electromagnetic waves. Now, recently, we also have the gravitational waves, which is detected, and then that opens up a different way of observing cosmic events and then things that's happening and matter that exists in the universe. But otherwise, it was electromagnetic interaction. So there are now clear evidence for existence of particles or matter which do not take part in electromagnetic interaction in the same way as what we have for the other particles like protons, etc. They are called dark matter because they don't really have electromagnetic radiations, electromagnetic interactions. So they are not seen. We don't see them directly. But their existence or their presence is now very clearly established. Well, I mean, the observations are still, yeah, anyway, so let me don't go into non-particle physics explanations of dark matter. There are things like that also, but as far as particle physics are concerned, and we are thinking that everything can be thought about as made of small elementary particles, then these dark matter is a completely different type of particle. It has to be a completely different type of particles. So these two, one, Barium Asymmetry of the universe, then the dark matter, and then there is also something called dark energy. I don't want to get into that, but that's a different form of energy and not the usual energy. Okay, so these are the things that we have. We know they are there, now they are established, but we don't really have any theoretical understanding or no models, or no whether the standard model of particle physics or standard model of cosmology or any other model do not really give a consistent way of accommodating all of this. Well, there are phenomenological models and then ways that people have suggested. There are many ways. Some of us are actively working in such these dark matter, Barium asymmetry, etc. And that's one of the things that we don't but have a good understanding of. So let me don't go on. Let me also, I think I have spent about 20 minutes already. So this is kind of the motivation that we have for this course. So further on, I think it will be again interesting to learn about elementary particles. And I think we will discuss some of the dynamics of that, and then in terms of what's called the Lagrangian, etc. And also talk a little bit about the standard model. And maybe in the next live sessions, we can talk more about or a little more involved things about those things, and also about their participation in the cosmological models, etc. Right? Yeah. So I had a look at the questions that some of you have put up. Okay, so let me read these out. Some questions are not about the physics part, so that I think I will leave out. I don't think I will address that now. But if you want, you can send me a mail or we can chat. If you really want to ask again in this session itself, you can ask me and then we can discuss that. But a few of these physics questions are like, what are the exceptions in nuclear shell model? How can we account for them while filling the nuclear? Well, see the way that we had developed, we took different potentials to actually get this energy levels, right? So what we have in the final this one with including this orbital coupling, right? Is that is the kind of thing that we have as a final thing that shell energy levels that we can think about. I don't know whether any finer details, more refined models are there are some little bit more refined things to actually accommodate, especially when you go to heavier nuclei, okay, to take care of those things. They are there. But basically, for odd A particles, nuclei, it is a good way to understand the nuclear dynamics, or the shell model gives a good description of the energy levels, the filling of these things, etc. Okay, but if it is a even A, then we don't have an odd. See, the shell model actually says that everything is filled whenever we have these particles pairs of these nucleons, then they don't really take part or show up in the nuclear properties like the nuclear spin or the parity, etc. Rather, it is basically the odd one. If there is one odd nucleon, either the proton or a neutron, which is there, then that would be the one. All the properties of this shell or the nucleus will be decided by that. Not all, but at least spin and parity would be decided by that. So if we have even a particle, even a nucleus, then there won't be any, well, such odd nucleon that we can think about. Even we can actually have odd Z and odd N, but there are two of them. So there is a question about how do we actually combine these properties of these protons and neutrons together. And so there are other things that are to be added there. So that's one of the things, especially in the case of even Z and even N, it's even more visible that we will definitely have to actually take into account the interactions of these nucleons if we want to actually get a realistic picture. Okay? But for the ODA nuclei, it works well. Okay, especially the lighter ones and medium heavy, not very heavy ones, but medium ones. So that is how it is. If you have anything specific on that, you can ask me again. Then the other question is exothermic process. I don't know in which context you are talking about this. Usually the exothermic means giving out energy. So, but we can chat. If you can tell me what exactly you have in mind, and then I can try to discuss that. How do we define most energetic or less energetic alpha particles? I don't know. Again, what exactly is the meaning of the question? I didn't understand. But basically, what the energy of the alpha particle will depend on what is the Q factor, right? How much of the mass difference is there between these? Yeah, the Q factor, that the way that it is defined, right? So this is, so basically you have the daughter when the parent nucleus will decay to an daughter nucleus with the emission of alpha particle. So it depends on the binding energies or the masses of this parent and the daughter nucleus. So you have to find out what is the Q factor, and if the Q factor is large, then you will have more energetic alpha particles, right? That's how it goes. More energetic, less energetic will be like if the Q factor is very small. Again, if you have something else in your mind, you can ask me, and then I will. And cascade down. I don't know in which context I must have used it. Cascade down usually is to say that, okay, one reaction happens, and then maybe if you are talking about the cascade reactions, like an element, a particle, a
During
nucleus.
the beta particle decay, sir.
Yeah. Oh,
During
yeah.
beta particle decay.
Yes, in the beta decay, you have one particle, one nucleus, which is radio active and beta decays, and you have a daughter nucleus, which is also not a stable particle. Then that also undergoes maybe a beta decay or an alpha decay or whatever. So let us take a beta decay. So X beta decays to Y beta decays to some Z, like that. Okay, so that is the kind of cascade decays that I must have used. And so there radioactive rules are to be taken into account. I mean, it should take into account the decay of the daughter particle as well. When we are asking questions like, how many daughter particles are there after some time, after a minute, or after a few seconds, or after a day, or whatever, then if it was the stable particle, it would stay there. So we don't have a question about it. We can just wait for a long time, then it will get accumulated and you can count them. But if that is not a stable particle and decays, then after some time it also decays. So the number of that particle will also come down. So the radioactive rules for that that has to be taken into account. So together, for both of these together, we'll have to actually look at slightly differently compared to when the daughter particle is a stable particle. So that's where we use this. Why are we
So
not?
during the electron capture.
Yeah, electron cascade. Yeah, beta decay or any. It doesn't matter whether the daughter particles are beta decay, undergo beta decay, or positron emission, or whatever it is, alpha decay, whatever it is. It doesn't matter. It will go into something else, right?
Okay, sir. And also I have a question about exothermic. Like when I was studying the alpha decay, that I
Hmm.
got the point exothermic process. So I want to understand it.
Alpha decay.
During alpha decay, I was studying alpha decay process, so I got the point exothermic process. So that point I don't know. So I want to understand it.
Okay, you can just tell me, send me that reference or wherever you have exactly what is the context. Basically, exothermic means giving out energy, which means that um, initial particle will have larger energy compared to the final thing, or larger mass compared to the final one. So it will give out energy. But you send me that whatever you are reading.
That means the showing that the Q factor, the Q value is greater than equal to zero in the sense of exothermic process, and
Yeah,
the
usually
mass
it is.
defect is greater than equal to zero.
Yeah, right. But
And,
basically, hmm, just send me this thing because giving out energy, whether that particular thing is talking about beyond what the alpha particles. Sometimes what happens is that the particles which are the daughter particles are not really in the ground state. It can be in the excited state. So then also it can give out energy additional to that. The gamma decay can be there. So just send me the context and then I will look at it. Okay, and then we can discuss. Send me an email. You have my
okay.
email?
Yes, yes, sir.
Yeah.
Yes. And actually, sir, I have a other question like most energetic alpha particle and less energetic in the what sense do the most energetic and less energetic alpha particle like actually all alpha particle are same, I think. So how we define this is the most
Uh,
energetic, that was the less energetic, what we see in the in this sense.
in a particular reaction, you are right. The alpha particles come out with the fixed energy.
Yes, sir.
Yes. But in different reactions, you can have more energetic, or I mean, the energies of the alpha particles can be different.
Actually, that means depend on mass. So mass will
Yes.
be different.
It will depend on the mass of the parent particle and the daughter particle,
Oh, okay, so
right?
this is the reference of B.S. Martin book, like Introduction to Nuclear Particles.
Ah. So it's if you are talking about, I'll check that thing, what context it is saying. But basically, if you are talking about different reactions, then you have larger Q value, which means the difference in the mass of the initial and final is large, then you can have more energetic particles, alpha particles. Compared
And actually, sir,
when the mass difference is small, the alpha particle will be produced with lesser energy compared to the other process.
oh, thank you.
Yeah, yeah. So others, okay, there was Ashok. This is Abhiram who was speaking, right?
Yes, sir.
Okay. Then, yeah, Pranay had this question that I told earlier, exceptions in the nuclear model. So you have something more? Are you there?
Yes, sir, I got what was said. I was just thinking in terms of like the higher masses there, do they follow exactly the energy levels?
Yeah, no, I mean, you may need corrections, yes. You need corrections to those. The more refined version of the shell model has to be used for those things, yes. It's not 100% that it will be. I mean, even the spin and parity will not be exactly as predicted by the shell model for heavier particles. So basically, they do actually account for. So what is done is then you do take into account interactions of the nucleons in the periphery in certain shells, etc. So there are more refined versions of this. Okay. Okay. So Ashok has a question on why are we not considering impact of gravity in the movement of particles? Is it negligible to? Yeah, it is something which you can find out yourself. For example, you take a proton and a proton, okay, or a proton and an antiproton. Just take proton and proton. They will repel electromagnetically, right? And that repulsive Coulombic repulsive force, you can try to find out how much is that electromagnetic interaction. They also have mass, so they should have gravitational interaction. They do have gravitational interaction. And you know the Newton's equation, Newton's gravitation interaction, the force law, right? Similar to the Coulomb interaction law. So use that to find out the gravitational interaction. Now you have to replace this electromagnetic coupling with the Newtonian gravitational constant, right? So you will see that it is much weaker. How much weaker, etc. You just find out. It's some 3-4 lines of calculation, right? Take your simple calculator or your mobile calculator, and you can compare these two. The electromagnetic interaction of two protons divided by the or the force. You take the force, okay, in Newton, divided by the gravitational force of attraction between the protons. Fix the distance at some whatever distance, because that's going to be cancelled because it is both have 1 over r square thing. So that will not come in. Then the masses of this proton and mass charge of the proton, put in all those values, and you get the answer. And let me know what the answer is. Send me a mail saying that, yeah, I found out that this is my answer. This is the gravitational force divided by the electromagnetic force is this much. And you will see that it is negligible. Is that okay, Ashok? He's not there? Okay.
Yeah, that's fine, sir. Yeah,
Right.
I got it. Yeah.
Now, so anybody else have other questions? Somebody has written that they have a question, but what is the question? Yes, you can ask me. All right, so we have some time, 20 minutes or so. So, any clarifications, anything? Okay, non-physics things also you can ask. Some questions were like.
Sir, one general question, sir.
Yeah.
Today you talked about the existence of particle and antiparticle coexistence. So does it have anything to do with the, the entanglement and stuff like that, what we hear? Or
not really directly. So, but they will have all those things because they are quantum states. And when they are produced, maybe what you have in mind is like when they are pair produced, whether they will be entangled or not. Yeah.
exactly, yeah.
So usually it could. Sorry. So the entanglement of these two, like yes, they do their spin and things like that could also be, if you are considering, they could be in an entangled state or otherwise also. So we don't really in experiments, for example, we don't really for some reason have to worry about that. It's not really, the entanglement does not really play much role. For example, let's see, when we are producing proton-proton collisions, right? And then you can produce electron and positron. So the entangled state of electron and positron is not really something which will be seen at the detector level. So I mean, it kind of get washed out. I think it has to be coherent state to actually see those things. So we won't really have that kind of a thing. That's what I think. So because the detector interaction of these electrons and the positrons with the detectors will not really be able to be sensitive to those kind of a thing. So to see the entanglement and do the experiments with the entangled system, you really have to have special yeah devices or special methods. So
what will be an example of such kind of an entangled particle? Which
well, there are this. I mean, if you there are people who are actually doing these experiments on the entangled states, like photons can be in an entangled state. That's one of the things that they do. So photons, they can be in an entangled state. You can generate them, you can study them. Okay. When you detect these things, then yeah, it's basically it is the spin states. That's one of the things that it will be sensitive to the entanglement, sensitive to the entanglement. But you can actually check the details of the experiments. Okay, just Google a little bit about the quantum entanglement or the experiments based on that, etc., and then you will see. But in particle physics, we don't really have to worry about those things as far as the particle dynamics and the measurements related to that is concerned. But the entanglement is is one of the important things, which we do know that there are entangled states now. There are experimental support, experiments which are actually established that entangled states exist. This itself was not sure in the early days of quantum mechanics, like in the first part of 20th century, for example. But after the Bell's studies and then in more recent experiments have actually shown that quantum entangled states are there. They do exist. And in fact, the whole of the basis of quantum computation is such entangled states.
Yeah.
So a lot of research is going on in that. It's a very interesting topic, in fact, and not understood. The basic idea of quantum mechanics or quantum physics of that is not understood really. Although we know how to compute, etc. Okay. Yeah.
Okay, thank you.
Hello, sir. Hello, sir.
Yeah.
Sir, please say about muon G2 physics. Like this is not belongs to the course, but I want to know about it.
Yeah, we actually maybe we will defer it. Ask me in the next session. By then, I think we will perhaps have a little more understanding of the interactions of the leptons, etc.
Yeah.
G-2 of the muon is one of the anomalies things in the sense that the theoretical prediction and experimental observations differ considerably.
Yeah.
It's not very
Yes.
simple. So, and that's not just one measurement. We have been living with this for last 10 years or more now. And that, therefore, people are now taking it very seriously, thinking that there are things that to account for this, we need to actually go beyond what is described by the standard model of particle physics, is the thought that we have now. But I will tell a little more about it in the next session or next to next session. Yeah, maybe next session itself. Just ask me again, okay?
Okay, sir. Yeah, someone calling about this is the new physics, like new.
Yeah. It is, could be, I mean, how do we account for, how do we say that new physics would actually explain it, etc.? I mean, so to say that, we need to understand a little more about the elementary particle dynamics. So just wait for a little while. I don't know, where are we now in the course? It's around the quark model and things like that, right? We will go to the electromagnetic interactions at some point, I think. After that, we can actually discuss this. How the new physics.
I will mail, sir. I will mail.
Yeah, sure. Akila, you wanted to ask some question. Not there? Okay. Others? Yeah, so what is the level of this thing? Some of you had been telling that it's a bit, the questions are slightly little tougher side. Is that correct? I mean, do others also feel the same way? The assignment, for example, you're all okay?
Sir, some questions in the assignment are considering some exceptions which are not exactly discussed in the video lectures. So that is one issue which is there.
Yeah, I mean, but it is related, right? And one of the things that we would do is to see. I don't think there are many of that, right? Are there too many of those?
No, sir, one or two per assignment.
That's actually deliberately put because, I mean, it's something which you may be able to explore and then find out, right? So that's what we want. We want a bit of this going beyond what we are discussing in the course, but not too far around that, but a little beyond that thing is encouraged. So those questions are put into actually encouraged. I mean, so that you can actually look up and discuss among yourself. Or you can also send me a message to see that, okay, how do we do these things, etc. Even before submitting the assignment, if you want to have Well, not the answer, of course, but if you think that a particular question is not is beyond what is really discussed in the lectures, and if you want to know how to handle that, first discuss among yourself, find out your friend group possibly, or discuss with the TAs, put a forum discussion of the matter. So some of you may know the answer, then you can reply, or otherwise the TAs will tell you what is the kind of thing that can be done, etc. But that I would say, don't jump into doing that. That there should not be an easy way of dealing with it. Okay, I don't want to Google, do the hard work of finding out how to do it or think about it. Let me ask them so that they will tell me. So that shouldn't be the attitude. Okay, but you can still, after exploring yourself, you can ask us. All right, Mohammed, you wanted to ask something?
Yeah.
Yeah.
Yes, sir. Basically, sir, after due date is over, you may be please give the manual solutions for that, because some questions are there which I got the answer and the key was something different. But I repeated again and asked the TAs, but my answer is maybe correct, maybe incorrect, but I need to know how did the answer arrive at that.
Yeah, so we will be publishing. In fact, the assignment 1 is already out, I think. The answer, right?
Yeah. Yes, sir.
Answer to assignment 1 is already out, I think. 2 would be also out. So we'll give you all the assignment solutions. All the assignments solutions would be put up after the due date.
Yeah, basically we need to get the point that why did we wrong.
Obviously, yeah, that is the idea. So for assignment 1, it's already out. That's my understanding. If you don't see it, let me know. For other assignments also, we will put it up. Okay. And some of these things, for example, I think the question 1 of assignment 2, that's what I remember. We had gotten the key wrong because it's a typo. Basically, instead of answer A, then we put the B, the other way around. I don't know. So that what we will do is to actually reevaluate those things. Last year or the year before also, sometimes I have gone completely off also, like all of us, the TAs and I also overlooked some of the things and then we got the answer incorrect. Now that questions we will withdraw. So don't worry about those things. You will have a chance to look at the solutions. And
for example, in assignment, yes, sir. Yeah.
You will have a chance
Yes,
to
sir.
look at these things. And if there are errors in the questions or keys or anything, that will be taken.
Yes, sir. I would have, I have some question for assignment 2. Question number 1. What is the expected spin value of the ground state of nucleus calcium-2043 within the nuclear shell model? I got answer as 7/2, but the key is 5/2. But in no way I got, I came up to the 5/2. I repeatedly got 7/2.
No, you are right. Actually, 7/2 is correct. Yeah. We are going to reevaluate.
But my answer was there wrong.
No, that will be reevaluated.
My answer was put at TAs, maybe evaluator has put that as wrong.
Basically, the first evaluation when it is done, once we upload these things, then we can't edit it. It's automatically done. Okay. It's
it's automatically done.
But what we do, there is something called a re-evaluation. So that can be done only after the due date, and that will be done for these questions. Is what I'm telling you. So don't worry about that part. Okay.
Yeah, basically after due date of that was a week ago, 1 week ago.
Yeah, I know. So it is
like another question for the activity of the sample. I got repeatedly one answer, but the key is something different.
Yeah, so you can put it in the forum.
Yeah.
And we will look at the question also again. And if that was wrong, then whatever we find we will immediately put it like this 7/2 we already knew. So that's going to be reevaluated. Okay. So whatever mark that you lost now, you will get back. Don't worry about it. Similarly, if there are other questions that you think, then put it in the forum or ask the TAs or tell the TAs, and then we will look at that question again. And if there is an error, we will correct it. So that is how it goes. So in the first evaluation, you may not get the mark, but in the re-evaluation, you will get the mark. If you are right.
I discussed the same question with the TA, and she assured that next week we will discuss that.
Yeah.
Yeah. Thank you, sir.
Yeah. Any other thing?
Yes, sir. Please, you may be uploading the notes, sir. No, sir.
Notes, yeah,
Slide
there
notes.
already. Because I mean, I have some not very. I mean, it's not edited version. I have a non-edited version of this transcript, which is what I have been actually uploading as the note. So that should be there already. So with all that, it should be there. I will check with the NPTEL guys, and they should be able to publish it or make it available to you. It's already there with them. I will ask them to give it. Okay.
Thank you, sir. Thank you.
Okay, so thank
Sir,
you all for joining. Yeah. Yes, Abhiram.
okay, sir. Sir, I have a question on my magic number.
Huh?
Magic number, sir.
Yeah.
Please say about magic number.
What is the question?
What is the magic number actually?
Well, it's just a way of saying, in the sense that some of these nuclei with certain A values, A numbers, atomic numbers, are exceptionally stable. Okay, found to be exceptionally stable, observationally, experimentally. Experimentally, in the sense that they are very stable. They are observed to be very stable. So there was this question about why those numbers, and it was not like any other these things. Isotopes of atomic numbers. Sorry, what is this? Mass number, not atomic number. Mass number 8, 20, etc. Okay, so they were therefore called magic numbers in the early days when we did not know why that is so, etc. But in the shell model, the way that we look at it and fill these things, then there is this larger energy gap. We can also compute the energy level between these shells, right? So you will see that between these or wherever these shells are filled in the way that A is equal to 8, 20, etc., then the next energy level is higher, much higher. Okay, so this is the kind of thing that that is the way that the nuclear shell model would actually explain it. But in the initial days, it was called. I mean, that name then stuck there. It was called magic number because those A values are exceptional, or the isotopes with such A values are exceptionally stable. So it was called the magic numbers.
Yes. And sir, what is the successful model of nuclear model, like a cell model, liquid drop model?
Yeah. So, for example, I mean, it is shell model is a successful model, especially for lighter nuclei and odd A ones. But then certain properties like the electric dipole moment, the magnetic dipole moment, electric quadrupole moment, etc. That also depends on the distribution of the charge. But
Charge,
in the nuclear
yes.
cell model, there is no charge distribution that we talk about. So there is this collective models, liquid drop models, etc. are as for those properties. So they are more useful. So it's a kind of hybrid models that are more successful there. What one will actually take into account for certain properties, these things, and the nuclear interactions and the collective behavior for certain other these things, etc. Nuclear physics is also like more involved than, I mean, what we have done is a very, very, very simple elementary part of that. This thing. In fact, I should uh, uh, confess that I don't know much about the research level activities in the nuclear models, because it's an involved um, active area of research where finer details of these shapes and the exact values to matching the magnetic dipole properties, electric quadrupole properties, all those things are done, and various other properties of these things, etc., are all done. Are and people are working in that. Okay, but I don't really work in that area. So for me, I mean, my personal interest lies elsewhere. So I know that such more refined models exist. But if you are interested in knowing more about it, I can try to find some references and then or see if somebody else is there to help you out with that.
Okay, sir. Okay, sir.
Okay.
And
So
one
thank
and one request, sir. Please organize early the next live session.
sorry.
Uh, the ne-
I think the idea is that every month we will have one.
yes, sir.
So the date, etc., will be announced later.
Well, okay, sir. I will mail, sir.
Yeah, all right. Yeah, you
Okay.
mail that
Thank you.
thing. Okay. Thank you all for joining. Have a nice time, and then let me know if anything further is there. Send me a mail. Don't just hesitate to send a mail independent of the forum. Okay. Bye bye.
Thank you, sir.
Bye, sir. Take care.
Bye.